Thank you very much for introduction. And today, maybe I just want to, so what I'm talking about may be quite remote from the theme of this conference. So therefore, I want to make my talk not so boring as much as I can. So today I want to talk about this Lagrangian Floer theory. Maybe with a focus on Toric case. So after this is actually based on joint works with Kenji Fukaya and Yongen O and Hiroshi Ota. And if time permits, I may also mention our joint work with Mohammed Abzaid. So, okay. So the story is the following. So for instance, if I consider this S2, S2 is just a two-sphere like this. And then I consider the height function, maybe height maybe here 0 and height 1. Certainly it is a momentum map for the rotation action. And then for this, we consider some function like PO of S2. Y is equal to Y plus T over Y. And this T is actually that T in this lambda, so it's actually indeterminate. And for CPN, the function P of CPN, y1 yn is equal to y1 plus yn, and T over y1 yn. So this is a function, and so I will explain a little bit about this Lagrangian Floer theory, but somehow in this Toric case, this function somehow knows the Floer homology. In other words, after we consider the critical point of this one, and then we can see where the Lagrangian submanifold which has non-vanishing Floer theory. So maybe I just start things. So X omega be a closed, that is compact without boundary symplectic manifold. So namely, omega is a closed non-degenerate two form. So locally, as everybody knows, locally this omega is written as a dxi dyi, and I 1 to 1 to n. This is a double theorem. And then I take J, it is almost complex structure, such that if I define the bilinear form using this symplectic form and this almost complex structure, and then I have a bilinear form, and then I assume that this is a Riemannian metric, namely symmetric and also positive definite. So such a thing always exists because the group of linear symplectic transformation contains unitary group as a maximum compact subgroup, as you know. And so this is a first thing. And then secondly, I consider maybe two submanifold, so-called Lagrangian submanifold. So namely, they are just half-dimensional. submanifold so that this omega relative to this submanifold completely vanishes. So this is a Lagrangian submanifold. Maybe I consider only the closed one, so compact without boundary. And then somehow the Floer complex. So it may not be a complex in general, but I just want to tell what it is. So maybe I denote by CF, and maybe L1, L0, and delta. So this one is a free module generated by intersection point. And so the original work of Floer, actually he considers the free module over Z over 2Z. But today I consider everything over this lambda, or maybe lambda 0. So what it is? So this is something like a Laurent series, but exponent, just real numbers. So if it is an infinite sum, then the exponent diverges to infinity. And then if you consider the case that all the exponents are non-negative, it gives you subring. And its unique maximal ideal is this lambda plus, namely all the exponents are positive. And then it has so-called variation. So it's a non-Archimedean setup. So you take this element, which is non-zero, then some coefficient is non-zero. So therefore, I take a minimal exponent of it. So that gives us some additive variation. Okay, and so free module, maybe today I only consider over, maybe today lambda 0 or lambda. I consider both cases. And this delta somehow count so-called J-holomorphic strips joining two intersection points. What does it mean? So maybe I also have to, I plan to use only one blackboard, but somehow it's not good. So maybe I just use this. Okay. So namely, I consider just a strip like R times 0, 1. It is actually sitting in the complex plane, and this is the real axis, and this is a part of the imaginary axis. And then I denote this tau and t, and then going to x. So I consider mapping like this with several conditions. First one is a Cauchy-Riemann equation. So like I have almost complex structure, so therefore we can consider this equation. So this is something like a Cauchy-Riemann equation. And then the second one is a boundary condition. So tau I belongs to Li, I maybe 0 or 1. And the third one is this U tau t, and tau tends to plus minus infinity. Then this one is equal to p plus minus. So namely, I have some manifold X here, and then I have two Lagrangian submanifolds like this, L0 and L1. And then I have a cylinder like this. And then I consider mapping from here to here like this. And then, so this part may be mapped to this. So lower boundary is mapped to L0, and upper boundary is mapped to L1. And then if tau tends to negative infinity, and then it converges to the intersection point. And then if tau tends to plus infinity, it may converge to another things. And so maybe I consider this as P plus P minus, a solution of all such things. But then it has obvious symmetry, because we have a translation symmetry, because this equation is symmetric in tau variable. And so therefore, we can shift in tau direction. And then if I assume that, maybe I didn't really say this, if I assume that they have a spin structure, and then I can also give an orientation on it. And also, we have a dimension formula for this guy. So dimension is actually given by the difference of so-called mass of bit of indices at this point, minus 1. Minus 1 coming from here. But anyway, so I only consider case that, at this moment, I only consider case that this MP plus P minus is equal to 1. And then the boundary operator is the following. So delta of Q is equal to the sum of MPQ and P. But more precisely, I may write it in the following way. So maybe I take a equivalent class of U from this MPQ. And then here I take P, and then take T, maybe I need some sign here. And then I also have a just area of this holomorphic disk. And so this is delta. And so Floer actually, he considered the case of Z2 Gradic, Z2 coefficient case. So not this lambda case, but he showed that this delta square is equal to 0 if pi 2 of xli is equal to 0. But in general, this delta composite itself is non-zero. So I can give you a very easy example. That is, you have just a line here, and then I have a small circle here, like this. And then I have two critical points, intersection point, and P and Q. And then I have one orbit like this, one strip like this, and also I have another strip like this. And so starting from P, going to Q with some decoration, and then Q back to P with some decoration. So therefore, in fact, in this case, delta of P is equal to the P, but T of the area of this guy, this thing. So it means that some sort of holomorphic disk is obstruction of this guy. So what we considered is the following things.
So this is supposed to be a
So if you like, maybe you can also put it here.
Yes.
Well, maybe torus anywhere.
Thank you.
And so what we did is the following. So formulate obstruction to this thing in terms of this filtered infinity algebra of this Li. And I will explain it now. And then the second thing is that when and how can we rectify delta? So we add some correction terms to this operator so that the delta square equal to 0. So here the keyword is kind of bounding cochain, or maybe even weak bounding cochain. And so another word is weak Maurer-Cartan element. And also we have further construction, so-called bulk deformation. Maybe I may speak about it shortly. So filtered infinity algebra is the following things. So in our case, actually we consider some vector space. Maybe in this case, maybe you forget upgrading, but vector space over the ground field. And then I consider some module which is defined in this way. And then the filtered infinity algebra structure B is the collection of multilinear operators over this lambda or lambda naught, k run from 0, 1, so on. In fact, this M0 is somehow responsible for these kind of holomorphic disks. And then, so I wanted to write this, but very hard. So like M1, maybe I don't really write everything, but maybe I write something. And sorry. This one is equal to 0. And if I consider this thing, so it's a binary operator, and then apply this M1. And then certainly we have term like M2, M1, C1, C2, plus minus M2, C1, and M1, C2. If it is equal to 0, it looks like Leibniz rule. But in fact, we have more terms, like M3, M0, and C1, C2, plus minus M3, C1, M0, C2, and one more term, namely M0 is the last one. So this one is equal to 0. Yes. So it is a kind of Leibniz rule, but with these terms. And then we have M1, M3, plus da-da-da-da. So this last one is somehow, if M0 is not present, then it is associativity for M2 operator up to M1 coboundary. So last one is somehow, I don't really so if M1 is M0 equal to 0, then it's associativity up to homotopy. And then I have an infinite many such relations. So this is a filtered infinite algebra. And how can we define such a thing, construct such a thing? So take any relative homology class. So like L is a Lagrangian, X is ambient space, and then consider holomorphic disks in this class. So that we denote by M, k plus 1 beta. So in fact here, I have to consider so-called stable compactification, stable map compactification. In fact, it is not really a compactification. We have to consider moduli space of stable maps, border swab maps, but somehow it's just abuse of notation, so abuse of notion, so stable map compactification of moduli of holomorphic disks with k plus 1 boundary mark point. What does it mean? So I consider some disk, say, and then I have a boundary map point like this. And then map to here I have L, and then I have mapped like this. So this is a mapping like U here. And then over here, I have a bunch of evaluation maps. Namely, if I have U, and then I can consider U of Gi, and this gives us element in L. So this is this evaluation map. So I have a k plus 1 evaluation maps. So namely for each at each things. And so, for instance, if I take this V bar as a drum complex of this L, well, more precisely, I have to shift degrees, but maybe I will omit this. But anyway, so I take here from C1, Ck, and then I consider mk beta of psi1 that psi k is equal to evaluation 0 streak, kind of integration along fiber, and then L1 star C1 that Fk star Ck. So namely, I put back differential forms from here, and then somehow push out the differential form to this. And here, this space may be very ugly space. So therefore, to make sense of this, we need so-called virtual technique. Which Kenji, Fukaya, and I developed maybe mid-90s, and then further developed by our work. And so this one is also integration along fiber. Certainly, if it is not submersion, usually you cannot define it. But somehow, in this technique, we thicken the space and then make it submersive. And if you take thickening, then you have a kind of normal bundle, and then you take a Tom class of that. And then somehow you wedge with the Tom class and then take integration of fiber or something, and then we can actually make sense of this. So this is a mk beta operation, and then our mk is equal to the sum of mk beta and then t to the power the area of the homomorphic disks. And this summation taken over beta. And if we don't have this, it may be infinite sum. So therefore, the sum may not make sense, cannot make sense. But we take this one, so-called Gromov compactness, somehow guarantees it converges in such a t-adic topology. So this is our mk. And then this one satisfies this sort of equations. So simply because if you consider disk, certainly I have to also consider mapping like this. But then if you look at the limit, so limit is somehow looks like this, right? Maybe this is 0 and this. So the limit may be like this, right? So the boundary of this guy is kind of this. And then this part is already some M operation. So number of things is K0, K1, then MK1 operation. And then now it's the input, and then I have a bunch of another K2, many boundary mark points. And then this is actually MK2 operation. So therefore, we have such a quadratic relations. So this is a reason why we have such a thing. Okay. So now, okay. So now I tell you a little bit more. So what is a bounding chain or bounding cochains? So B, maybe I take it from H. Sorry. Maybe I have to say this. So originally our MK, maybe in that case, actually it is defined on the Ram complex of L, tensor with lambda 0, and tensor K to this same thing. But so you have such kind of things. And then actually we can also, using some algebra, kind of homological algebra, actually we can also cook up some operation on the homology of cohomology of this guy. So this construction we call the canonical model of this guy. Okay. So this one is also filtered infinity algebra. Okay. So if you have such a thing in chain level, then we can also squeeze the structure to there. And then I take B from, maybe in this case, H odd of L tensor lambda 0, and then consider MK B of psi 1 psi k. So I think this formula should be kept. So this one is obtained the following. So MK plus L0 LK, and I insert arbitrary number of B's like this. And so it is also infinite sum. So this L0, L1, LK, maybe anything. So this is infinite sum. So it is easy to consider the case that this has a positive, that maximal ideal. And then if you have so many B's, then the exponent T getting bigger and bigger. So therefore it's very easy to see that it converges in Toric topology. But we can also do little thing. So namely, this one is equal to C times lambda plus. And for this part, if I only consider H1, so not the whole odd part, but H1, and then we can twist it by local systems. Maybe I don't have time to do this, but we can put some local system over Lagrangian manifold, and then we can twist all constructions using holonomy of that. And so therefore we can handle this. And if you consider higher degree things, then some sort of dimension counting argument also help us to define this. But anyway, so this is the one. And bounding cochain or Maurer-Cartan element is the following. So this one is M0 of B is equal to 0. So because if you consider the DGA version of this, then that may be d psi plus psi equal to 0, something like this. So it looks like a Maurer-Cartan equation, so therefore, yeah, it is that one. And then we call it is weak if it is not 0, but it belongs to the lambda plus times the unit here. So this is unit. Okay. So this is the one. What is good is that in these cases, so like if I I introduce these things, then I can put B everywhere. So everywhere I can put B here. And so if M0B is equal to 0, then we don't have this term, so therefore it has satisfied some Leibniz rule. And if M0B is equal to 0, then we have associativity after homotopy. So in this case, it's very easy. And also, if it's proportional to the unit, so I don't really explain the notion of unit in this infinity algebra, but the same, so if you have a unit, somehow some cancellation happens, so therefore we have the same thing. So in this case, actually, we have M1B is equal to 0, and M1B and M2B satisfy Leibniz, and M2B is associative product up to M1 homotopy. Maybe M1B homotopy. Okay. Okay, so this is the case. And so here I say that this is a Floer complex for L1, L0, but delta square may not be 0. Right? So, but I consider only the case that CF and LL, so the same thing. It's kind of self-intersection Floer theory, or maybe more generally we can consider bottomless type Floer theory. And then here, if I take this M1B, then from here, actually we can define self-intersection Floer theory. This self-intersection Floer harmonics. Because M1B square is equal to 0. And so this one, so if you move one of the, so it's a self-intersection, so therefore LB, LB. And if you move one of them by so-called Hamilton isotopy, and then we have a notion of not only filtered infinity algebra, but filtered infinity bimodules. And using that language, somehow we can also show that this, so if I deform it by Hamiltonian perturbation, then the Floer theory become isomorphic if we take this coefficient lambda. So lambda 0, it is not really isomorphic, but going to lambda, then they are isomorphic. So that's the things. Okay. Okay, so now I come to the Toric case. And Toric case, I want to compute something. Okay, this is okay. So I have still 25 minutes or something. So maybe before this, I want to introduce a notion of potential function. So potential function, maybe this very strange notation, but maybe we use this PO. And this is a function defined on the so-called weak bounding cochain, with weak Maurer-Cartan element. And then here I don't really want to explain anything, some sort of gauge equivalence. And this our function PO is defined over here, or maybe even plus. So this is the following. So I said that M0B is proportional to unit. That's a definition for the weak Maurer-Cartan element. That coefficient is this function. So this is the definition. So weak Maurer-Cartan element is the one so that M0B is proportional to the unit. That proportionally constant is the value of the potential function at that point. And so if you have two Lagrangian manifold, and then if we have two such weak multi-Cartan elements, and then we can somehow deform the original Floer's boundary operator using two weak multi-Cartan elements. And then this delta square is not necessarily 0, but that is equal to the difference of potential functions. Difference of potential functions. So somehow, if we fix one of them, we get so-called matrix factorizations by our construction. But anyway, so this is. So now I consider Toric case. And then I want to come back to this. So in this case, it's a good thing is that it has symmetry. And so far, I don't say anything about symmetry. But here, in this case, we have a maybe action of the compact torus on the symplectic manifold, maybe compact Kähler manifold, compact Toric Kähler manifold. And then we have so-called momentum map. To the dual of this Lie algebra. And sometimes I identify this with the, sometimes I identify it with the cohomology of the torus with real coefficient. And certainly it contains H1 of T of Z. It's a lattice there. And so now, so here after we use pi for the momentum map. It's very strange notation. People often use mu for this momentum map, but mu is kept for so-called mass-free index in this kind of stuff. So therefore, we couldn't really use mu here. So therefore, I use pi, and then I define the image of the momentum map. So this is a polytope associated with this compact Toric Kähler manifold. Okay. So now I take view from the interior of the polytope, like this one. And then the level set is a Lagrangian manifold. So that is our LU. So this is Lagrangian torus, and because it's kind of fiber of this, so maybe we often say Lagrangian torus fiber. But also this is Lagrangian torus orbit. And so torus acts there simply transitively, so we can identify with these things. And now we have H star of this L. So this is a torus invariant differential forms, space of torus invariant differential forms. And certainly it's also algebra. And this is in this situation, certainly it is identified with the ordinary cohomology of this one. And so in general, we consider maybe some Drown complex and so on. But because in this situation, if I consider this M of k plus 1 of this beta, right? And beta is H2 of x LU Z. So this is actually torus orbit. And therefore, the torus acts here. And therefore, every construction, like pull back by aberration map or push forward by aberration map, everything is actually T equivariant. So therefore, we can work on this level. So in this case, actually, we don't really need to do this algebraic process from this cochain level to cohomology. We can directly define our operator on this space. Okay, and also we can say that for any B inside of this H1 of LU, so again, using this kind of symmetry, so we can show that this one is always weak bounding cochain, so weak Markov-Cartan element. So I need a little time to explain this, so therefore today I just omit, but it's not so hard to see why it gives us such a weak Markov-Cartan element. So in general, we don't know how to find weak Markov-Cartan element, but in this situation, actually, we can get lots of weak bounding cochains.
Excuse me.
Yes.
Are you considering the T equivariant homology or non-equivariant?
This one is non-equivariant.
Thank you.
This is non-equivariant.
So you just use the symmetry, but
Yes.
in the non-equivariant
Yes.
setting. Thank you.
Okay. So we have this operator, and so in this situation, we have this M1B, which is a differential, and M1B and M2B satisfy Leibniz rule, and M2B associative up to MB homodom. Okay. So now I consider the following things. So B, maybe I just write it as, sorry, maybe I take a basis. Sorry. Maybe I should write here. So let EI be a basis of maybe H1 of LU of Z. And then I consider B in that H1, so therefore it can be written as Xi and EI. I run from 1 to n, and Xi just run to 0. And then I consider the function like PO, B, maybe LU. And then I compute its derivative. So B is this guy, so I plug in B here, and then differentiate in this. But what is this? So this is equal to ddxi, and this one, so sorry. Maybe better to write one more thing. So one more thing is just this one of LU. Okay. And then this is equal to ddxi, and then I say that this is actually M0B, right? So I want to compute this. But M0B is that one. So in the top of the blackboard, I wrote this MKB. If k equal to 0, then I have no size. And so therefore, I only have B's. So that means this is actually ddxi, and then sum of mk and b, like this. And then I differentiate in the direction of EI, right? Certainly this one is multilinear, so therefore this one is equal to the sum over k and sum over j equal round from 1 to k of mk and b somewhere, and then EI and b. Maybe this is a J's place. And then, if you look at this, compare with this formula, this M casings. Now k is equal to 1. You have k equal to 1, and then you have only one psi, rest are all b's. So exactly this one. So therefore, this one is equal to M1b of this EI. Okay? So I said that maybe we just look at some critical point of this guy. So if it is a critical point in a certain sense, and then M1b vanishes. Okay? So B is a critical point of the POLU. Then, so actually this is if and only if M1b is equal to 0 on this H1 of LU, maybe lambda 0 or something. Okay. But now, remember that our M1b satisfies Leibniz rule, and so we have also Leibniz rule, maybe associativity up to homotopy. And now I use one more data, that is, if I consider cohomology of, ordinary cohomology of this LU, and this is actually the torus, so this is actually generated by H1, by cut product. As an algebra, it is generated by H1. And our M2b is somehow equal to the up to sign, it is actually cut product coming from the constant map somehow, modulo maybe lambda plus times. So using this, somehow if M1b vanishes on H1, we can automatically say that the M1b vanishes on the whole thing. So using this thing, actually we can actually show that this M1b is equal to 0. But M1b is an operator acting on this cohomology of LU. So therefore, this one is same as this HF of this LU, and B is isomorphic to the torus, cohomology of torus. Right? Maybe here I take lambda 0 coefficient, then I need to take a tensor plot with lambda 0, and if you take a lambda coefficient, then this is with lambda. So therefore, finding a critical point of this function, we can see which U, I mean, so in this situation, U is chosen. So first U chosen, and then ask whether you have a critical point or not. And in this case, this is in this form, right? Maybe I have to do a little bit more. So the next thing is that this yes. In fact, maybe to write it precisely, maybe it may be a bit difficult, not so difficult, but I started from this X omega J. This is a compact toric Keller manifold. And I have this pi, T star, and then P is inside here, and then U is a point in the interior of this guy, and so on. Okay? So now I have this potential function of LU, but actually we can have a potential function of X, and which is defined on this. Let me explain this. So this V is this one. But now I consider H1 of LU, sorry, H1 of the torus, okay, H1 of the torus, and here I have lambda minus 0. Okay. And then I have just a linear extension of this guy. So then I get it to H1 of the torus of R. And then this is certainly same as P star. And here I have P. Here I have P, interior of P. Right? So, and this one is in fact lambda minus 0 to power n. Okay. So this one is contained here. So, okay, so I have this function. Maybe I can explain it with that example. And okay, so let U equal to sum of Ui of EI, right? So this is the element in this P circle, and then therefore it is inside of P star. And so I have such a description. And so what is the relation between these two functions? P O L U of y1, yn. And this one is equal to, sorry, maybe I forgot to say one thing. But maybe let me do it first. Okay, y1 and t u1, yn t un. So the statement is that the statement for claim is that for compact toric scalar manifold, there is a function like this, so that for each u, we have this potential function at u, and that is actually written in this form. So this is just one function here, and then instead of y1 to yn, we plug in them here, and then this. So in this case, if this level is u, and then potential function of Lu is equal to y times t u plus t1 minus u over y. Because this area is u, and this area is 1 minus u. So this is the area of holomorphic disks. So therefore we have this. So now let me put it like a new y. And then this sum is equal to y nu plus t over y nu. So this new variable, this is our potential function on S2. So this one. Okay. So somehow all the potential function for Lagrangian torus fiber can be described by using just one function P of x, but using this. And then I also just make one remark. So maybe 5 minutes. Okay. So okay. So now I consider critical point of this P of x. Let's consider y here. And then y may be y1, yn or something. And then uy is equal to the v of y. And let's also write it as u1, un. And then by is actually a logarithm of y1 t minus u1 logarithm of yn times t minus un or something. So then hf of L of uy and by is isomorphic to the homology of the torus. So this is another statement. So it's just restating the statement there. But here, actually, I have only one function. So just a function associated with the toric manifold. And important thing is that the y should belong to this B vector inverse P circle. So that is important. And then you take variation of it. Then you can see which Lagrangian is actually have non-vanishing Floer theory. Okay. So this is a critical point theory. And I have no time to say about bulk deformations. But if I say a little bit, so bulk deformation is actually so using ambient cycles with lambda 0 coefficient, we can deform these M casings. So maybe cycle may be written as both B, and then this thing is MKB or something like this. And again, this H1 of LU of lambda 0 is contains this weak Markov space. And we have potential function, so hence we have a potential function, so on. So now I consider the following things. So I have a cohomology of the ambient space with lambda 0 coefficient, and then map it to so-called kind of Jacobian ring of this function. Maybe if I need this B here, and then maybe to put B here, maybe I shouldn't really put it. Oh, no, okay. So this is but definition is the following. Here you have this A, and then I just consider potential function of B, and then deform it in the direction of A, and then differentiate in this parameter, and then take its equivalence class in this. So because Jacobian ring is somehow you have a Lorentz series and modeled by the Jacobian ideal, and here it's more complicated stuff. We need to use some non-Archimedean stuff, but somehow we can consider this one. And this is what somehow we call the Kodaira spacer map. And if I have B and I have B here, and in fact, important thing is that if we consider the product of this one, but maybe we take so-called quantum cohomology of this guy, and then this is after isomorphism as an algebra. So this is a theorem. So quantum cohomology can be described also this one. And from here, maybe I have to stop now. But from here, actually, we can some argument. So like, for instance, if in this CPN, so here we have this function. And then the critical point of this guy has a variation, which is in this case, it's kind of barycenter of the polytope. And so-called monotone Clifford torus. So now you have a Lagrangian manifold with non-vanishing Floer theory. We don't know what it is. You consider Lagrangian manifold with non-vanishing Floer theory. Then it must intersect with this monotone Clifford torus. That result follows from this one, and also the result obtained with Mohammed Abzaid about split generation criterion for the Fukaya category. But maybe I have to stop now. Thank you very much.